In 1971, Stephen Hawking suggested that a mini black hole from the early universe could be lurking at the center of the Sun. His proposal was extended in 1975 by Don Clayton and collaborators who suggested that the power generated by the infall of matter onto such a black hole could explain the observed deficit in neutrinos of the electron flavor from the Sun. This deficit was known at that time as the solar neutrino problem, formulated by calculations of my early mentor, John Bahcall. Having a second power source in addition to nuclear fusion would have naturally reduced the production of solar neutrinos through nuclear reactions and accounted for the neutrino deficit. Nevertheless, could the Sun still host in its belly a primordial black hole that does not contribute much to its luminosity? After all, we know that 85% of the matter in the universe is invisible. Primordial black holes with a mass similar to that of asteroids in the size range of 1 to 100 kilometers could account for dark matter. If this is the nature of dark matter, is it possible that some stars captured primordial black hole in their belly? If so, what would be their fate? It is easier to address the second question. A black hole captured by a star could change its evolution and internal structure. The interiors of stars can be diagnosed through their oscillations, just like the use of seismic signals to probe the inner structure of Earth. The unusual evolution and interior structure of stellar hosts of mini black holes could be searched for in the future. Given the high speed of dark matter in the Milky Way, the likelihood that the Sun captured a primordial black hole is 1 in 10 million. Nonetheless, given the hundreds of billions of stars of the Milky Way galaxy, there could still be tens of thousands of Milky Way stars which have captured a mini black hole. Because of the smaller characteristic speed of dark matter in dwarf galaxies, most of the stars embedded in ultra-faint dwarf galaxies could have captured a mini black hole. After consuming their nuclear fuel, the core of Sun-like stars contracts to make a white dwarf, a metallic sphere roughly the size of the Earth. Since the radius of the Earth is 100 times smaller than the radius of the Sun, the average mass density of white dwarfs is about 1,000,000 times larger than that of the Sun. The accretion rate of matter onto an embedded mini black would therefore increase 1,000,000 times, potentially igniting the white dwarf and triggering a supernova explosion. Rare explosive transients of a new kind could be searched for in the data pipeline of the Rubin Observatory, which will start operations next year. The effect of a mini black hole would be even more dramatic if it is trapped in the core of a massive star with more than 8 times the mass of the Sun. Such a core collapses to make a neutron star after consuming its nuclear fuel. The density of the neutron star resembles that of an atomic nucleus, 100 trillion times higher than the mean density of the Sun. Under these circumstances, the primordial black hole may be regarded as a seed that grows to consume its host star and transforms it into a stellar mass black hole. This channel could lead to black holes with the mass of a neutron star, an outcome which is not expected under normal astrophysical evolution. Currently, the LIGO Virgo Cagra Observatory identifies compact objects as neutron stars or black holes by their mass, identified through their gravitational wave signal. The existence of a neutron star channel to a black hole would cause confusion in this identification scheme and result in events where compact objects of neutron star mass are detected in gravitational waves but release no electromagnetic radiation due to the absence of matter. Primordial black holes make up dark matter, then the nearest black hole would be inside the solar system. Having a black hole close to home opens an opportunity to study quantum gravity experimentally. A black hole with an event horizon the size of a proton would radiate spontaneously. If we ever witness an asteroid mass black hole in the solar system, it can be used as a testbed for quantum gravitational experiments on a subatomic scale. Understanding it would guide us in developing a predictive theory that unifies quantum mechanics and gravity. Having such a theory would in turn inform us of what might have led to the Big Bang, and knowing that would bring us closer to appreciating our cosmic roots. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.